Welcome to this explainer. Okay, let's jump right into this, because today we are mapping out a definitive, absolute blueprint for mastering the construction of logic expressions from problem statements. If you are preparing for Cambridge computer science examinations, you already know the stakes are incredibly high and the scenarios can be brutally complex. I want you to picture a real Cambridge past paper question. Maybe it's an automated greenhouse system or an abstract robotics factory. Now I want you to picture two types of students. Let's call them Alex and Sam. Alex is the kind of student who overloads their answer with every raw computer science fact they've ever memorized, completely ignoring the analysis part. They just dump data onto the page. Sam, on the other hand, rushes right in, starts drawing gates, and completely misses the specific command word requirements in the prompt. When the examiner gets these papers, they're just covered in red pen marks. We are not just going to review the basics today. You already know your ands, your ors, and your not gates. Instead, we are going to look at the precise architectural framework examiners expect to see when you translate a dense, unfamiliar text problem into a flawless logic expression. This is about building bulletproof arguments with stress-tested evidence and total quality control.
So let's look at the number 15. This single topic commands your absolute, undivided attention because it accounts for a massive 15% of your total marks in Paper 2 for the 96-18 syllabus. That is not just some tiny margin of error. 15% is literally the difference between two entire grade boundaries. When you master this, you are effectively securing a massive chunk of your final score right out of the gate. It's an incredibly high-yield area, which is exactly why we are dissecting it today. And honestly, whether you're tackling syllabus codes 0417, 0478, 0983, 0984, 2210, or sitting the advanced 9618, the core logic underlying these examiner expectations remains absolutely consistent. You need a system that works every single time, without fail.
But before we go ahead and secure those marks, we really have to ask the fundamental question that plagues so many test takers when they flip open that exam paper. Why do students find applying concepts to unfamiliar contexts so hard? Think back to Alex and Sam. You can know the theory perfectly in a vacuum. You can draw a logic gate from memory perfectly. But the second Cambridge introduces a scenario about a totally novel chemical plant temperature sensor, absolute panic sets in. The translation from plain English to a mathematical logic expression suddenly feels like staring up at a sheer cliff face. Alex tries to climb it by throwing random facts at the wall. Sam tries to sprint up it and slips immediately. We need to figure out exactly why this happens, and more importantly, how to fix it permanently.
Today, we are going to completely deconstruct this exact challenge. We are going to look at 4 distinct areas to build up your exam strategy. First, we'll dive into the core principles, where we break down specific command words and how to respond to them. Second, we'll explore the procedural framework, giving you a step-by-step methodology for tackling the paper. Third, we'll uncover the critical examiner traps that catch out thousands of students every year. And finally, we'll master critical analysis and evaluation, which is where you pick up those elusive top-tier marks.
Let's move right into our first agenda item, the core principles. This is where we build the foundation of your theoretical architecture. And this is exactly where we reveal the ultimate strategy to fix the mistakes that students like Alex and Sam make. To stop throwing random facts and to start answering the actual question, you need to decode the command words. Are they asking you to describe, explain, analyze, or evaluate? Each of these specific computer science assessment objectives requires a totally different approach. If the prompt says evaluate, but you just describe the logic gate, you score 0 for that section. It really is that brutal. The syllabus makes something abundantly clear across the board. Top-performing candidates don't just rely on rote memorization. They showcase a connected, conceptual understanding that seamlessly adapts to entirely new, unfamiliar scenarios. To do this, you need to use the PEAL framework. That stands for point, evidence, explanation, and link. Make your point, back it up with evidence from the scenario, explain how that evidence proves your point, and link it back to the original question. That is exactly how top students structure their computer science answers. Now, imagine a split screen. One answer just lists facts, the other uses PEAL. It takes about 30 seconds to spot the difference, and the examiner sees it instantly. Before we continue, subscribe to our YouTube channel, Ace the Exams, at @ACExams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. To effectively use that PLL framework and achieve true mental agility, your conceptual framework needs to encompass a few highly specific pillars. First, you need precise definitions, knowing exactly what your logic gates and operational symbols mean without hesitation. Next, you need a firm grasp of causal relationships. If input A triggers a high signal, how does that cascade through the system to output B? You also need systematic analysis and evidence-based reasoning, which means deriving your logic straight from the problem statement text provided in the exam. You can't just invent variables. You have to use exactly what Cambridge gives you.
And here is the final pillar, which is essentially the ultimate cheat code directly from the examiners themselves. Principal examiner reports highlight that candidates referencing cross-topic connections achieve significantly higher marks. If you can tie your logic expression back to data representation or hardware architecture or algorithmic design, topics you've studied across codes like 0417, 0478, or 2210, you are signaling to the examiner that you don't just know the topic in isolation. You understand the entire ecosystem of computer science. Actively integrating these connections into your explanations will noticeably elevate your score and push you into those top-grade boundaries.
Now that we understand the theoretical goals in the Peel structure, let's move into the transformation phase. We are jumping into Section 2, the procedural framework. Theory is fantastic, but we need a rigid, unbreakable system for the exam room. Think back to Alex and Sam's heavily red-inked papers. If we sit down with them and guide them to rewrite their answers live, utilizing a step-by-step procedural framework, we can literally watch those red pen marks transform into green check marks. This is the computer science success blueprint.
So what exactly is this blueprint? This is your standardized, non-negotiable battle plan for tackling these questions. First, deconstruct the prompt line by line. Underline the command words. Second, extract the relevant data, especially pulling from any binary representations or variable tables provided. Third, select your analytical framework. Determine what type of logic expression or truth table is actually being asked for. Fourth, execute the working with absolutely clear notation. Do not rush this part like Sam did. And finally, present your findings using the correct terminology. Every single one of these steps is designed to add specific marks to your paper. Do not deviate from this sequence.
The crucial reason why we rigorously enforce that exact sequence is because it activates what we call the method mark strategy. This is an incredibly vital approach where you secure marks simply for demonstrating your process. If you just jump straight to the final logic expression and make one tiny error, let's say you accidentally drop a NOT gate or mislabel an OR gate, you could lose everything. But if you explicitly show your systematic process and your clear working on the page, the examiner can award you partial credit, step by step, even if your final conclusion has a flaw. You are literally harvesting points along the way, turning a potential 0 into a 3 or a 4 out of 5. To ensure you don't blank during the test and skip these crucial steps, try this memory hack. You need to use a visual story method to encode this exact procedural sequence into your memory. Imagine physically tearing apart a question paper, that's deconstruct. Imagine pulling glowing binary 1s and 0s right off the page, that's extract. Visualize choosing a specific tool from a heavy tool belt, select framework. See yourself writing with a bright glowing green pen, execute. And finally, imagine presenting a golden plaque to the examiner, present. I want you to set a mental timer for 60 seconds right now and attempt to visualize that story. It guarantees the procedure becomes second nature under extreme exam pressure. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
With our procedure firmly locked in, it's time for an interactive workshop. We must navigate to Section 3 and analyze the critical examiner traps that cost students dearly. Let's start with Challenge 1, the data scan. Imagine a complex computer science data source pop up on your screen right now. Maybe a dense truth table or a highly complex graph of logic gate outputs. If I gave you a 60-second visual countdown timer, could you extract the core trend without getting overwhelmed by the noise? The trap here is that students get bogged down in irrelevant data and miss the core logic pattern the examiner is actually testing.
Let's move to Challenge 2, find the flaw. Cambridge Principal Examiner reports have generously identified the top 3 fatal errors candidates make year after year. First, applying the wrong algorithm or logic structure for the context, basically using a hammer when you needed a scalpel. Second, forgetting to check boundary conditions and edge cases. In logic, what happens when all inputs are 1? What happens when all are 0? If you don't check those extremes, your expression is fragile. And third, providing generic answers. If I show you a flawed sample paragraph right now, I guarantee the sentence losing marks is the one that sounds like it was copied straight out of a textbook without referencing the scenario.
Let's zero in on that last point because it is the absolute ultimate trap. The examiner alert literally reads, "The classic mistake is providing generic answers not specific to the question context." If your written justification or your logical breakdown could apply to any random question you've studied across 0983 or 0984, it is guaranteed to lose marks here. The examiners design these specific scenarios, like a factory conveyor belt or a chemical plant temperature sensor, for a very specific reason. You must use their terminology, their variables, and their exact conditions.
This comparison brilliantly illustrates the divide between average and exceptional. Struggling students fall into the classic trap. They drop a generic, memorized definition disconnected from the scenario and just hope it scores points. But the top performer, they anchor absolutely every single analytical point directly back to the unique scenario in front of them. Let's do challenge 3. Speed writing. If you had a 30-second timer right now, could you write one perfect peel paragraph? You'd make your point, bring in evidence from the factory scenario, explain the logic gates function in that specific context, and link it back to the system's overall goal. That is how you prove you are a top performer. Context is absolutely king here.
We are in the final stretch now. Let's move to Section 4, Critical Analysis and Evaluation. We are going to look at the complete computer science answering system that pulls everything we've learned together into an actionable cheat sheet. This is about taking your mark potential from a baseline 0 all the way to 100%. When you hit these higher-order assessment objectives, you aren't just solving a problem, you are critically evaluating it.
So here is the final system. Your ultimate problem-solving sequence should follow this deconstruct, solve, evaluate loop. You identify the given information, break it into logical steps, and solve it systematically. But then, and this is the critical higher-order step, you check for reasonableness. Does your logic expression actually make physical sense in the context of the automated greenhouse? Finally, you make justified recommendations. To guarantee top marks, you just need 3 rules. Number 1, command word decoding. Number 2, Peel framework application. And number 3, a time management matrix to ensure you don't spend 20 minutes on a 3-mark question.
Let's summarize exactly what examiners want for execution. When asked for a comparative analysis of different logic approaches, you cannot just list features. You must explicitly state both similarities and differences, using clear comparative connectives like whereas or conversely. Furthermore, you must connect every single point with evidence straight from the data. And when evaluating alternatives, draw conclusions about their relative importance and justify why one logic solution is superior. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
As you continue your preparation, the choice is ultimately yours. Will you fall into the trap of generic answers and rote memorization like Alex, hoping for the best? Will you rush past command words like Sam? Or will you execute this exact blueprint to extract maximum method marks from every single scenario? The logic expression you build next could legitimately be the difference between grade boundaries. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.